So today we're going to start talking about the composition of solutions. So in order to be able to do any kind of stoichiometric calculations, we have to know two things. We need to know what kind of reaction's going on, and we need to know the amounts of chemicals present. Now the nature of the reaction depends on the exact forms the chemicals take when they're dissolved. Do they take on ionic form? Do they take on molecular form? So that's the nature of the reaction. The amounts of chemicals present is generally expressed as a concentration. So think about, oh, this is strong coffee, this is weak coffee. We're talking about the concentration of the coffee or of the solute that's dissolved in the solution. So in science, we have a special way of measuring this, and that is something called molarity. So molarity is moles of solute per volume of solution in liters, and it takes on this form. We have moles, we have liters. It is actually just a simple equation, but there is another caveat that goes on to that, and that is that this is actually a conversion factor. You have something over something else. And so we've done conversion factors like this before when we've talked about molar mass, where you have grams per mole. This behaves just like that, except it's in moles per liter. So molarity tells us two things. It tells us the concentration of the solution, and it can also be used as a conversion factor to either tell us the volume of the solution or the moles that are present in that solution. It's very simple to use. It says calculate the molarity of a solution prepared by dissolving 11.5 grams of solid NaOH in enough water to make 1.5 liters. Well, we know that molarity is in moles per liter. And we know that we can take grams and we can convert that to moles. If we look on our periodic table, NaOH weighs roughly 40 grams in 1 mole. And when we do the math, it should come out to something like 0.2875 moles. We can then feed that into the equation to calculate its concentration or its molarity. So 0.2875 moles. And the volume has to be in liters, and you will see here that it's already in liters. So when we do that math, we get something that's 0.19, and then this capital M underlined means molarity. That is a capital M. It does need to be underlined, and the reason is that when people write, if I'm on just a white piece of paper, how do you know if this is a capital M, or this is a capital M, or this is a capital M, or this is a little m, or this is a little m? So we do it so that you know what molarity is. In textbooks, you're going to see an italicized M, but it'll still be capital. Now, you've heard me say back and forth, calculate the molarity, calculate the concentration. Molarity means concentration. So as long as you know that vocabulary, you're in good shape. Another example here, we could calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make 26.8 milliliters of solution. So again, we know molarity is moles over liters. We need to convert our 1.56 grams of HCl. HCl weighs 36.5 grams in 1 mole. And we can then get 0.043 moles of HCl. Now, the difference here is that our volume is in milliliters, so you need to convert that as well. You could do that a couple different ways. I prefer just moving the decimal place, 1, 2, 3. So I can now feed that into our equation, 0.043 moles in 0.0268 liters. And in the end, we get 1.6 molar solution. So the concentration of this HCl solution is 1.6 molar. Now, another neat feature is we can also calculate the concentrations of ions. So when ionic solids are dissolved in water, such as NaCl, you know that we have Na ions and we have Cl ions. And I have shown you, or we have talked about the idea that when things dissolve, it's these ions that actually react. It's not the whole compound. So we can describe the concentration of those ions as well, because we'll want to know how those ions are behaving in the reaction. So here's an example. It says 1 molar NaCl was prepared by putting enough NaCl in water to make 1 molar solution. However, when NaCl is put in water, it breaks into ions. So the answer to this all is how many ions do we have? We know that 1 molar NaCl is equal to 1 molar of Na plus ions and 1 molar of Cl minus ions. This is very similar to the conversion factors that you've used in the past where you've said, oh, 1 mole of CaCl2 gives you 2 moles of Cl. Same type of idea. This subscript will tell you how many moles proportionally there is within that solution. So here's an example, and you could do this a couple different ways. You could do this through straight up problem solving, which is what I'm going to show you here, or you can do it using dimensional analysis. So here they want us to use this given concentration and find out the ion concentrations in that solution. So we have two different ions here. We have CO plus 2, cobalt plus 2, and we have nitrate, which is a -1 ion. So if it's 0.5 molar of CONO32, that means that when this breaks apart, you're going to get 1 cobalt plus 2 ions and 2 NO3 minus ions. So if the whole solution is 0.5 molar, that means for every 1 molecule of this, you're going to get 1 molecule of CO plus 2 and 2 molecules of the nitrate ion. So hopefully you can see that you would get 0.5 molar of CO plus 2, the same as the concentration of the beginning solid, and you would have 1 molar NO3 minus because you have 2 NO3s times that 0.5 molar. Now you can also do this using stoichiometry. So let's just do the second example here. It says 1 molar FeClO43. We want to know how many ions there are. Well, if we have 1 mole, okay, so this, hang on, not stoichiometry, we want dimensional analysis. Let's do dimensional analysis. So we have 1 molar, or 1 mole per liter of the FeClO43. We know that for every mole of FeClO43, there are 3 moles excuse me, of ClO4 minus ions. So if we cross these things out, our solution will have a label of moles per liter, which we know means molarity. So the answer is 3 moles per liter. Again, you can problem solve that. For every mole of the Fe, you get 3 of those ions. So if it's 1 molar, that means of the whole solution, it'll be 3 molar of the perchlorate ions. Now if we go on to the next example here, it says calculate the number of moles of Cl ions in 1.75 liters of 0.001 molar zinc chloride. So you're used to having one number as your starting point, and that one number as your starting point is your given. But now you have 2 numbers in this problem. That first number is going to still be something that has a single label. That second number, even though it's molarity, remember that that's really a conversion factor of moles per liter. So since it's a moles per liter, that's going to be our conversion factor. So we're going to start with the 1.75 liters. We're going to then use the fact that there's 0.001 moles of zinc chloride in 1 liter. And then we're going to use the fact that in 1 mole of zinc chloride, there are 2 moles of chlorine ions. And so we multiply across the top, we divide by the bottom, and you should get 0.00, oh, you know something, my math is wrong here. 0.0035? I might be off by a power here. I forgot to multiply by 2 on my work that I did ahead of time. So check my math here. I don't think that's right. I might be off by a power of 10. But if we do all of our crossing off, we know that our units are in moles of chloride ions. All right, one more example. Typical blood serum is this kind of molarity, 0.14, we have 1 milligram of NaCl. So here again, you will start with the thing that has a single unit, 1 milligram. You should know that there's 1,000 milligrams in 1 gram. And now we need to get to somewhere that we can use the moles per liter. So to get to that, to get from grams to mole, you should be thinking to yourself molar mass. Now NaCl weighs roughly 58 grams in 1 mole. We know that according to this conversion factor, there's 0.14 moles in 1 liter. So if we do all of that math, we get 1.23 times 10 to the -4, liters, which you can then of course convert into milliliters, 0.123 milliliters. So it's handy to use, I guess you can call it stoichiometry or dimensional analysis to do some of these conversions, and you'll see how we're going to use those even more later on.